Number 12 courses 1 to 5 we had for homework last night. I want to do questions 4 and 5 on worksheet number 12. Question 4 says, calculate the apparent weight of a 65 kilogram person in an elevator that's moving upward at a constant speed of 3 meters per second. What are we really looking for apparent weight? What variable is that the same as? How heavy I feel? Not the same as gravity, it's the same as normal force, right? So we're looking for the normal force here, and it's a constant speed of 3.00 meters per second. Firstly, recognize what am I looking for? Normal force. Secondly, recognize that the speed that it's moving is irrelevant. The speed that it's moving is irrelevant. If it's moving at a constant speed, it's in a state of equilibrium. Forces must balance. If forces are balanced, what's the acceleration? 0. There is no acceleration here. We're going to set this up in the same way as we set up our other questions, but you're going to see that mathematically it ends up being easier. There's a force of gravity acting down, and there's a normal force acting up that's going to be the same value as gravity, right? Because it's moving at a constant speed. It's in equilibrium. Now, you could at this point say, wait a second, if I want normal force and it's the same as gravity, why don't I just calculate gravity? But and that's fine. If you showed me that work, that would be okay. But I'm going to do it in a little bit longer way, just to illustrate that our method works no matter what. We're going to say F net is equal to the sum of the forces, Fg plus Fn. F net is m times A. It's equal to Fg plus Fm. My mass here is 65 kilograms. What's my acceleration again? If it's moving at a constant velocity? 0. Gravity is 65 times 9.81. Is that right? Is that right? Not quite. You got to put a negative with that term, right? Because gravity is down. I don't care whether you put the negative with the 9.81 or right out in front of the entire term. The 65 doesn't make any difference. Gives you the same result. On the left-hand side here, 65 times 0 is 0. 65 times 9.81 is 637.65. And I'm going to take that 637.65 over to the left side by dividing. How do I take that over? Adding, right? It's adding a negative number on the right side, so let's take it over by adding a positive number on the left side. Now we're going to round that to how many digits? 65 is 3 digits, right? 9.81 is 3 digits, right? What if this said 3.0 meters per second? It would still be 3 digits, right? How come? Because we didn't use that 3.0, right? We're going to say this is 638 newtons. So in this case, my actual weight is the same as my apparent weight. If you're in an elevator, you always feel that heaviness when you start moving upwards, or that lightness when you stop moving, or when you start moving downwards. But it pretty quickly equalizes, so that, you know, after you've been riding in that elevator for a second or two, you don't feel anything different, right? It's because you're going at a constant velocity. When you're at a constant velocity, you're in equilibrium, force is balance, and the weight you feel, or the normal force, is the same as the weight you are, the force of gravity. The two forces balance. It's only when you're accelerating one way or the other do you feel heavier or lighter. When we go on a roller coaster and we go around a turn, how many people have been on a good roller coaster before? You go around a turn, right? You feel heavy, right? Why do you feel heavy? Because the track is pushing in on you. And that would be the normal force of the track. The faster you go, the harder the track has to push in on you. The bigger the normal force. So the faster you go around that turn, the bigger the normal force, the more you feel like you weigh. Okay, the bigger your apparent weight. Okay, number 5. Number 5 says a 300 kilogram mass is pulled upward by a chain. What's the force of tension in the chain if the mass is accelerating upward at 1.3? This doesn't have to be any harder than an elevator problem. In fact, it's exactly the same thing. There is a tension force acting up. We could call that the normal force if we want. Okay, tension acting up. We got a force of gravity acting down. Is gravity bigger or smaller than the tension force? or the normal force, if that's what you want to call it. Smaller, how come? Yeah, if it accelerates upward, the upward force has to be bigger. So the gravity force is downward is smaller. F net is equal to the sum of the forces, Ft plus Fg, or if you call it Fn, we would say Fn plus Fg. Right? It doesn't matter what you call it. M times A is equal to Ft plus Fg. We're solving for Ft. Mass is 300. The acceleration is 1.3. Gravity is 300 times 9.81, correct? All right? Almost. It's negative, right? Negative 9.81 or negative in front of the whole thing, doesn't really matter. We need a negative term. So let's find this now. 300 times 1.3 on the left side gives me 390. (300 times 9.81), I think nope, 2943. Is that right? Now we're going to take that over by adding, because it's subtracted on the right side. 390 plus 300 times 9.81. Oh, look at that, 3,333. You can imagine here if you're designing some kind of equipment to lift an engine out of a car, or you're designing a crane where you have to lift a certain weight. You can imagine how it might be useful to be able to do a calculation like this to determine how hard the chain needs to pull. Okay? If you're designing this piece of equipment and you use a chain that will break when 25 to 100 newtons is applied to it, that's not going to work. Right? You need a chain that's strong enough to hold 3,333 newtons. That make sense? Now, if you were an engineer, you would build in room for error, right? So if you needed to hold 3,333, you would probably want to make sure that your chain held 5,000, 6,000, right? Just to be safe. But theoretically, it only needs to hold 3,333. All right, where are we going to round that to? How many digits? 300 is 3 digits. 1.30 is. 9.81 is. Final answer should be 3 digits. 3.33. The fourth digit is a 3, so the third digit is going to round down, right? 3.33 times 10 to the... How many decimal places did we move this? 3? 3.33 times 10 to the 3 newtons. Let's take another look at another example here now, example number 8. This is similar to what you did in a lab 2 days ago, right? You have two masses, one's hanging over the edge, they're attached to each other via a string around a pulley. We want to find the acceleration of the system. There's a force of friction of 20 newtons here. How do we tackle this? Well, firstly, recognize that we have multiple forces acting on this object, right? When we have multiple forces acting on the object, draw a free body diagram. We have a force acting this way. Whoops. Let's try that again. We have a force acting this way. I'm going to call that Fg, the force of gravity acting on that object. By the way, let's number these, number 1 and 2. We also have a force of friction acting. Which way is friction going to act on that 2 kilogram object, left or right? Left. It's going to move to the right as a result of that 10 kilogram object pulling it down, right? So we're going to say that force of friction this way is to the left. I don't know how big right now the applied force is, so it doesn't really matter about the lengths of these vectors right now. What do you think the value of the force of gravity is here? M times G, right? Right, M times G. What mass do I use? The 2, the 10, or would I use 12? Think back to your lab. 2, 10, or 12? Nick? 10. It's the 10 that's being pulled on by gravity that causes this system to move, right? Gravity is pulling down on the 2 kilogram as well, but in the end, the gravity pulling down on the 2 kilogram has a normal force that cancels it. This one doesn't have a normal force that cancels it. So the only mass that matters here is my 10 kilograms times 9.81. That gives me 98.1 newtons. Now, I'm going to redraw this. It's not mandatory that you redraw this, and in this question, it's not even overly helpful. But as we get going in more and more questions, it becomes more and more helpful to redraw. Here's what I'm going to do to redraw it. I'm going to pretend that object number 2 and object number 1 are on one plane. I'm taking this object number 1, watch my hand here, and I'm just pulling it up like this. That make sense? We still have a force of friction acting this way. And now we have a force of gravity acting this way. If I'm pulling up object number 1 like this, then I'm pulling up the force with it. It's going to be 98.1 newtons. Is this question not like many of the questions we've already done now? So what if we have a pulley? We have 2 forces acting on this, 20 newtons, 98.1 newtons. We know how to deal with this. You had a quiz on this one day. You did well on that quiz. Carissa?
How come the negative or the 9.81 is negative?
That's a good question. How come the 9.81 isn't negative here? Right now, I've only found the magnitude of this force. When I straighten it out, you'll see why in a second there, okay? Okay, that's a great question, though. It will get answered. Let's set F net equal to the sum of the forces. FF plus FG. By the way, technically, there is gravity acting down on number 2 as well, and the normal force acting up on number 2 that cancel, right? I just chose not to draw them in because they cancel. I didn't want to make my diagram too cluttered. F net is M times A. FF plus FG. What's the mass here? Is it 2? Is it 10? Is it 12? Think back to your lab. What mass do I use when I'm multiplying M times A? The total mass, yes. I always use the total mass in M times A because the entire system is accelerating. Okay, only object number 1 has gravity pulling directly down on it. So that's why I use 10 times 9.81, but the entire system is accelerating, so I got to use the whole mass here. It's going to be 12 kilograms times the acceleration equals the force of friction, 20 plus the force of gravity, 98.1 newtons. Should there be any negatives in there? Should there? Look at my picture. Look at my green picture. I'm going to make friction negative. Now, watch carefully here. This is why I redrew it. If you look at your original diagram, friction is drawn to the left, right? That should make that a negative force, right? Gravity's acting, Carissa, gravity's acting in my original diagram? Downward. That should make that a negative, right? So both forces, gravity and friction, should be negative values, right? Because one's to the left and one's down. But they oppose each other. If they oppose each other, they can't both be negative, right? One causes the system to move one way, one causes it to move another way. So we can't make them both negative. The reason that I've redrawn this is because it makes it easier to see that one needs to be negative and one needs to be positive. Does that make sense? You could have switched them around and made friction positive and gravity negative. That would have been okay. I think, to be honest, the easiest way is to do it the way that I've done it, but the other way would have worked as well. Carry it? Yeah. So it can be useful to redraw. You can do it without redrawing it, but if you do, you got to make sure you pay attention to the signs, and it's harder to pay attention to the signs because negative, left, think of it as negative, right? Down, we think of it as negative, but one of them has to be positive because they oppose each other. Okay, so I'm going to say here, 12 times A is equal to negative 20 plus 98.1. That's 78.1. For some reason, I can't scroll down. That's okay. A is just equal to 78.1 divided by 12. We'll say 78.1 divided by 12 gives me a value of 6.5. 6.5, 2 digits, right? .5 meters per second squared. Now I got a positive acceleration. What does that mean? What does that tell me? It's speeding up, yeah. It's speeding up which way? In the positive direction. What did I define as the positive direction? This way, right? So the system is moving like this. To the right, this guy's moving to the right, this guy's moving down, but they're both moving in the positive direction. Does that make sense? I mean, logically, it has to be that way, right? Because friction's not going to cause it to speed up the other way. Friction's not going to cause it to start moving in the opposite direction. So, remember 3 things here that make this question just a little bit tricky. Okay, number one, when you're finding the force of gravity involved here, sometimes we even see 2 forces of gravity because there's something hanging off the other side. When you're finding the force of gravity, make sure you use the mass that is hanging, because the mass that's on the table is countered by the normal force, so it doesn't count in that mix at least. So that's the first difference that we see. The second thing that we got to be careful of is that in the net force, we're using the total mass. The 2 and the 10. And the third thing that I want you to recognize makes this a little bit different is that we want to redraw this. We want to redraw this so that we get the signs correct, the pauses and the negatives correct. Yeah, I would say, I bet if I had just said on my original diagram, what's my next step? F net is equal to the sum of the forces subbed into numbers. You guys, half of you probably would have made both of those forces negative. Well, one of them has to be positive because they oppose each other. All right, I would like to assign right now 3 questions on that worksheet that we've been working on. Specifically, we're looking at questions 6, 7, and 8. You got about 10 minutes to work on those in class. What you get done, great. What you don't get done, you're going to finish up for homework.